Olá a todos, meu nome é Ítalo Brasileiro, eu sou aluno de doutorado do professor André Drummond e hoje eu vou mostrar um trabalho aprovado no ICTON, International Conference on Transparent Optical Networks, desse ano, e esse trabalho faz parte da minha pesquisa de doutorado. Então, desde já agradeço pela atenção. E ao final dos slides eu coloquei meu e-mail, então sintam-se livres para entrar em contato, tirar dúvidas ou qualquer esclarecimento. Obrigado. Hello to everyone, my name is Ítalo. I am a student at the University of Brasilia in Brazil, and today I'm going to show you our proposal for resource allocation in spatially multiplexed elastic optical networks. This is our schedule. At the beginning, I'm going to show some concepts around elastic optical networks. After, I'm going to present some definitions of spectral division multiplexing, and I'm show you how this concept is applied in elastic optical networks scenario. After, I'm going to show the definitions of the RMSCA problem and the crosstalk effect. After the crosstalk effect presentation, I'm going to present our proposal named Allocation with Strengthened Medium Core. And following, I'm going to show you some simulation results. And finally, I'm going to present the conclusions. So, elastic optical networks are defined as a type of network in which we can establish multiple circuits inside a single link. So we have inside the link the optical spectrum, which is divided in frequency ranges named slots. So inside a single fiber we can have multiple slots, and also elastic optical networks has the elasticity capacity because inside the spectrum we can arrange slots and put them together to create larger capacity channels for data transmission. This figure we can show some example of optical spectrum. Here we have a simple network with two nodes A and B, and between these two nodes we have a single link. Below we show this link spectrum. So we have here 48 slots, and these slots can be allocated to data transmission. So here we have three circuits as an example. The first circuit has one slot, and the slot number 2 is saved as a guard band to avoid interference between circuits. The second circuit in red has two slots, 3 and 4, also followed by a guard band. And next we have a circuit with 4 slots, from 6 to 9. So each of these slots has 12.5 gigahertz. In the elastic optical networks literature, there is a new technology which considers the application of multi-core fibers in the network's links. So instead of just one core, the links now has 7 or 12 or 19 cores, and each core has its own set of slots. So with the application of multi-core fibers, now we have more resources to allocate inside the network. In this figure, we show some examples of multi-core fibers with 7, 12 and 19 cores. To establish a new circuit inside a SDM-EON, it is necessary to allocate some spectral resources. For this specific type of network, we call this allocation problem as the RMSCA problem, which is composed by sub-problems, and they are the routing, the modulation selection, the core allocation, and the slot allocation. So the RMSCA problem represents the steps that needs to be taken for circuit allocation inside STM-EON. In this figure, we show some example of the RMSCA problem. The first step to solve the problem is the routing problem. So we need to find the best route for the new circuit. And in this figure, if you want to establish a circuit between nodes 1 and 5, we have two shortest paths options, which are 1, 2, 5 and 1, 6, 5. After the route selection, we can proceed to the next step, which is the modulation selection. The modulation is applied to the signal, and strongest modulations needs to be selected for circuits with longer distances. After the modulation, we can choose the correct core for our circuit, and the core should be searched inside each of the routes link. And the last step is the slot selection, which should be chosen searching in the spectrum inside the selected cores. When I'm tempted to establish a circuit, we also should be aware of the crosstalk effect. The crosstalk effect occurs mainly between neighboring cores. So I have here 3 cores inside one link, core 1, 2, and 3, and the effect occurs in neighboring cores and also between slots with the same index. So I have here in index 1, slot 1, circuits established in all 3 cores. So in core 2, this circuit has 2 neighbors, so the crosstalk effect will be stronger in core 2. Also, the crosstalk effect will occur in core 1 and 3 in the same slot 1, but not so strong as it is in core 2. And we can see the crosstalk occurring in some slots in this example, and we can see also that the higher the number of neighborings a circuit has, the higher will be the crosstalk effect. The crosstalk equation, it is used in the literature in a lot of referenced papers, and we have 2 basic equations: the H equation, which is the increment of crosstalk per unit length, and the main crosstalk equation. So to define the H value, we need to consider some fiber parameters, which are defined in the fiber fabrication process. The first parameter is the fiber coupling coefficient, which is indicated by the K. After we have the R, which is the curvature ratios, then the beta, which is the propagation constant, and the W, which is the core pitch. So these values are fixed and defined in the network in the fiber fabrication, and so the H value is fixed. On the crosstalk equation itself, we have 2 important constants, which are N and L, and these values are not fixed because it depends of the route. So, considering the application of multi-core fibers in elastic optical networks and the crosstalk effect, we propose here an algorithm for resource allocation. Our proposal attempts to establish the circuits with higher tolerance to physical impairments in the central core, since the central core is the core that suffers more impairment. Also, the other circuits are classified and divided in the peripheral cores, so we can have some cores with only even circuits and another cores with only odd circuits. And by even and odd, we refer to the number of slots demanded by the circuit. And also, at last, our algorithm attempts to change the modulation applied to the circuit, and tries to apply a more robust or a more strong modulation without changing the number of slots. So this is the flowchart of our proposal. We consider that the routing problem will be solved by the Dijkstra algorithm. After choosing the correct route, the proposal tries to select the most efficient modulation for the selected route. After the modulation is defined, then we can know the exact number of slots that should be allocated for this new circuit. The first step is to analyze the modulation. If the modulation is one of the strongest, and here we consider BPSK and QPSK as the strongest modulations, then the circuit should be allocated in the central core. Otherwise, the circuit should be allocated in the peripheral core. If resources are found on the central core, then the circuit is allocated with the first fit policy, and so tries to allocate the lowest index slot available. If the circuit goes to allocation in peripheral cores, then the n is evaluated, and the n is the number of slots of the circuit. So if n is an even number, then the circuit should be allocated in cores of even index. And if n is an odd number, then the circuit should be allocated in a odd index core. If resources are found in the first core available, then the slot will be allocated with the first fit policy. If no resources are found in any cases, then the search will be performed in all the cores, and this selected core will be the one with the highest index available. And in this case, the slot allocation should be performed with last fit policy. If even in this case no resources are found, then the request is blocked. Otherwise, if resources are found, then the circuit will be established. These are the main configurations of the simulation scenario. We are using the ONS simulator, and we generate 100,000 circuit requests for each simulation, and they are replied 5 times. The routing is by the Dijkstra algorithm, and the request bandwidths are of 10, 100, and 400 gigabits per second. We are using the USA network topology. The picture in the slide. This is our first result, and here we measure the circuit blocking probability. So the circuit blocking probability is the rate of blocked requests divided by the generated requests. We can show here that our proposal has lower blocking, so it allows the establishment of more circuits. And for the lowest evaluated load, we have a blocking around 0.2%, 0.1, while the worst concurrent has a blocking around 1.5. And for the highest load, we have a blocking around 1%, while the worst case, which is the RF CASC, has blocking of around 3%. Also, we evaluate the bandwidth blocking probability, which is the rate between the blocked bandwidth, the sum of total blocked bandwidth, divided by the sum of total generated bandwidth. And here we can show that our proposal also has a smaller blocking. While the worst competitor has blocking around 7% for the highest load, our proposal has a blocking around 2% for the highest load. So, as conclusion, we can mention that the use of multi-core fiber ensures greater availability of resources inside the network links. And also, these resources might have some physical interference because of the crosstalk, which occurs between neighboring cores. For these scenarios, we propose an algorithm which considers these interferences as the crosstalk and attempts to allocate circuits in a better arrange. Thank you all for the attention, and if you have any questions, you can send me in the following email.